Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the next session on the series of video lectures on the subject of system programming with Linux. The title of today's session is Linkers Behind the Curtain and Creating Your Own Libraries. In today's session we will see how linkers merge multiple relocatable object files into a single executable. We will talk of global, external and local symbols and the rules followed by a linker to resolve symbol conflicts while generating global symbol table. We will create and use our own static library using the Unix librarian tool, and finally we will create shared object files or the dynamic libraries. Well, first let us discuss why should you learn the linking process. It will help you build large programs. Understanding linker will help you avoid dangerous programming errors like what happens when you create global variables with the same name in multiple object files. It will help you understand how language scoping rules are implemented. It will help you understand other system concepts like loading and running programs, virtual memory, paging and memory mappings. And finally, understanding linking will enable you to exploit shared libraries. The two main advantages of linkers are modularity and efficiency. And the linker actually do relocation and symbol resolution. By relocation, I mean merging code and data sections of multiple object files into the code and data sections of the final executable. And by symbol resolution, I mean how the linker associates each symbol reference with exactly one symbol definition. Before we move on to our Linux terminal to practically understand these concepts using a sample program, let's discuss it on the slide first. Well, dear students, this time we will have divided our source code in two files instead of one, main.c and swap.c. The linker not only links main.o and swap.o to create the executable, but at the same time may also link the final executable with some library code as well, as shown over here. And we all know that a library is a pre-compiled set of functions ready to be used by programs. And we have static as well as dynamic libraries. In case if our executable is statically linked with a library, it can run on machines not having that library. But static linking do have its own limitations as well. Like, if you statically link your program with a library, the size of the executable on disk will be quite large. Moreover, when statically linked programs run in the memory, the library code is duplicated in all the processes. For example, suppose you are executing 10 C programs and all of them are using the printf library function. So 10 copies of printf functions will be there in memory. Last but not the least, if there is a newer version of this static library, all the executables need to be explicitly relinked. On the contrary, if we use a dynamic library, all the executables does not need to be relinked in case of a newer version. Well, the dynamic library does not suffer with any of the limitations I have discussed so far. Size of the executable on disk will be small, as it will not contain the code of the library functions but just a reference. In the memory, multiple processes share the library code, so only one process will have the code of printf library and is shared by all other processes. That is why we call the dynamic libraries as the shared objects as well. Last but not the least, dynamic libraries allows us to do version independent linking using the real name, so name, and the linker name of these libraries. So an executable is linked with the most up-to-date minor version automatically. Let me take this opportunity to tell you that the dynamic linking can be done at two times, as shown over here: the load time and the runtime. In case of load time dynamic linking, which is the default case for Linux, the library code is not, if the library code is not already loaded by another process, the loader loads the code in the process address space. And if the code is already loaded, the loader do not load it, rather just put the address at the place of the unresolved reference inside the memory. Well, load time dynamic linking is the default case, which is handled by the Linux linker LD. As far as the runtime dynamic linking is concerned, in this, the executable is loaded in memory with unresolved references, and the library code is loaded at runtime by the programmer himself using the DL open and DL close library calls. The runtime dynamic linking is normally used in high performances web services and other services which require high performance. Let us now move on to the Linux terminal and do a bit of scuba diving to understand the linking process in detail. The two tasks that every linker performs are relocation and symbol resolution. Let us first try to understand what relocation is. Well, we have the two programs, main.c and swap.c. Let us first create the relocatable object files, gcc-c asterisk.c. We have the corresponding 2.o files. Let us now link and create the executable, gcc asterisk.o, and let me name it myexe. We have the myexecutable file. Okay, so let us move on to the slide again and see the relocation process pictorially first. You can see over here the relocatable object files, main.o, swap.o, and maybe some other system relocatable object files that need to be linked. And we have one executable file over here. You can see the .text and data sections of main.o and swap.o over here are merged into the .text and .data section of the final executable. Let us see this over here. Let me use the obj dump and let me see it in Intel format, main.o. Note the addresses start from 0 and go up to 33 hex. Let me see the disassembly of swap.o as well. And over here as well, you can see the addresses move from 0 to hex 3e. Now let us see the disassembly of the final executable. And the final executable is myexe. And let me pipe it to less. You can see the disassembly of .init section first. And then you have underscore start. And if I keep moving down, you have, yes, over here you have the disassembly of the .text section, and we have the main over here, and you can see the different addresses. And then we have the disassembly of swap, and once again you can see The address is 68E. The instruction of the first address of swap instruction over here is 68E, while in the .o files it was 0. Well, dear students, since this executable is dynamically linked, the addresses will again change when this executable will be loaded inside the memory. And this is what relocation is. Let us quit, clear screen. And now let us try understanding the second task that every linker performs. That is symbol resolution, or how a linker merges the symbol tables of all the .o files and create a global symbol table for the final executable. Let us again move on to the slides and see the three types of symbols in the context of linker. We have global symbols, symbols that are defined in one module and can be referenced by other modules. These are called global symbols. External symbols, global symbols that are referenced by a module but are defined in some other module are called external symbol. Normally they are declared with the extern keyword. And the local symbols, symbols that are defined and referenced exclusively by a single module. For example, any global variable or function declared with the static keyword is private to that module. So while understanding symbols, you need to keep these three types of symbols in mind: global, external, and local. Now let us move on to the terminal again and understand these symbols by reviewing the code of main.c and swap.c. Let me do cat main.c. Well, the code has been taken from the book Computer Systems, a Programmer Perspective by Randall and David. Well, over here, this swap is a global external symbol because it is referenced in this module but defined in some other. For example, it is defined in swap.o. It is just referenced over here and used over here. This buff and this main, these two are global symbols because they are defined in this module and they can be referenced in some other module, and they are referenced in swap.o. Similarly, this printf symbol, this is a global external symbol because it is referenced in this module but it is defined in some other, maybe in printf.o in the standard C library. Let us review the code of swap.c as well to see the symbols. Swap.c. You can see this buff. This buff is an external symbol here because it is referenced in this file, that is swap.o, but it is defined in main.o. This pointer buff p0 is a global symbol because it is defined in this module. This buff p1 is a local symbol because the static keyword makes it private to this module. So buff p1 is private to module swap.o and it cannot be referenced anywhere else. This swap symbol over here is a global symbol because it is defined over here, while in main.o this swap symbol was the external symbol. Okay, so this temp. Well, this temp is a variable created in the stack frame of swap function and is called the automatic or stack variable. Linker knows nothing about this variable. The symbol table of swap.o module will have no entry of this variable. Okay, now you have a fair idea of the symbols used in these two files. Let us see the symbol table of these files. Let me clear screen. Let's see the symbol table for main.o first. We can use the read elf command -s option to see the symbol table of main.o, we can use obj dump command as well, dump with -t option to see the symbol table. And we can also use the famous nm command to see the symbol table. The output of nm is quite simple. You have just 3 columns over here: the virtual address, the type of the symbol, and the symbol name. Well, this buff is the global symbol in the initialized data section. This main is the global symbol in the initialized data section of initialized .text section. So that's why we have a T over here. Well, this printf and this swap, these two symbols are undefined in main.o, and they are external symbols. And we know that swap symbol is defined in swap.o and printf symbol will be defined in printf.o. So this is the symbol table of main.o. Let's see the symbol table of swap.o. Excuse me. You see, buff is undefined external symbol over here. As we have seen that it is a defined global symbol in main.o. Buff P0 is the global symbol in the initialized data section. So we have a D over here. Buff P1 is local to swap.o as it was declared with the static keyword. It is uninitialized, so it is placed in the .bss section. That's why we have a B over here. Finally, swap is the global symbol in the .text section. Okay, and now we know that the linker has merged these symbol tables, these two symbol tables, and have generated the global symbol table for the final executable. Let us see the global symbol table of myXZ as well. nm myXZ. You can see a lot of symbols over here. Okay. So you can see these buff P0, buff P1. The linker has merged both the symbol tables of swap.o and main.o to create the global symbol table. And finally over here you can see the symbol printf, which is still undefined because the linker has by default tried to dynamically link our executable with the glibc library, and once it will be loaded inside the memory, only then the definition of the printf function will be provided. So that's why you see undefined still over here. However, if I do this static linking, you will see a D over here. Let me do that as well. Let me clear screen. Let me use gcc -- static main.o swap.o, and let me name it myXZ2. Okay, let me say nm myXZ2, and let me do less. So you can see now this is a huge symbol table, larger than the one we have previously seen, and there is nothing undefined. You will not see any U over here. Everything is defined because this is statically linked. Okay, let's again move on to the lecture slides and discuss some more tidbits related to symbols. Well, this is a pictorial view of what we have already discussed, the code of swap.c and main.c, and the 3 types of symbols: global, external, and local. Well, this slide shows the structure of ELF symbol that is used by compiler to store a symbol definition. Actually, the symbol table is an array of these structs. Every symbol is stored in this struct. Well, the first member name is a byte offset into the string table that points to the null terminated string name of the symbol. Okay, now the question is, what if there are two symbol definitions with the same name? So there will be a name conflict. So let us discuss about the linker symbol rules as well. Well, dear students, the linker resolves symbol references by associating each reference with exactly one symbol definition from the symbol tables of its input relocatable object files. Symbol resolution is straightforward for references to local symbols that are defined and referenced in a single module that is declared with the static keyword. However, resolving references to global symbols that are defined in some other module and referenced in some other is a bit trickier. When the compiler encounters a symbol that is not defined in the current module, it assumes that it is defined in some other module and generates a linker symbol table entry and leaves it for the linker to handle. For example, in this code snippet over here, it will compile without any error or hitch. However, the linker will terminate when it cannot resolve the reference to this function foo, because the definition of this function is not available. Well, three types of linker symbols, global, external, and local, as we have discussed, are either marked as strong or weak. A strong symbol is a symbol that represents a function name or an initialized global, while all the uninitialized global are weak symbols. For example, in p1.c, this is a global symbol which is initialized, so it is strong. p1 is a function, so it is again strong. It is a global variable which is not initialized, so it is weak. And this is a function name, so it is again strong. Keeping the idea of strong symbols and weak symbols in mind, let us see the linker symbol rules. Well, Unix linkers use these three rules for dealing with multiply defined symbols. Rule 1 is multiple strong symbols are not allowed. Rule 2 is given a strong symbol and multiple weak symbols with the same name, choose the strong symbol. And rule 3 is if there are multiple weak symbols with the same name, choose an arbitrary one. Now let us move on to the terminal again and verify these concepts. Let me move up to the... Okay, so we have an example over here. We have a program that comprises of two source files, f1.c and f2.c. Let's see f1.c and let's see f2.c. So we have two source files, each having a strong symbol main. In this file we have a main, and in this file as well we have a main, which is a violation of rule 1, that is, multiple strong symbols are not allowed. We can of course pre-process, compile and assemble this program. Let me do that. gcc-c asterisk.c. You see we have the .o files. However, once you try to link these, the linker will fail, Before I link, let me show you the symbol table. Obj dump -t f1.o. You can see this main, it's a strong symbol. We have a G over here. And let me do f2.o again. We have this main symbol, and it is again a strong symbol because we are having a G over here. Let me clear screen. Let me try to link now. f1.o, f2.o, and let me name it myxz. And you see the error. The linker gives you an error, that is multiple definition of strong symbol main is not allowed. Let's see another example. In this example again we have two files, f1.c and f2.c. Let me do cat f1.c and let me view f2.c as well. You can see in this file we have a strong symbol x with the value of 1, 2, 3, 4, and in this file we again have a strong symbol x with the value of 1, 2, 3, 4, or rather 2, 3, 4, 5. And of course, as I have mentioned before, we can pre-process, compile and assemble successfully. However, we will not be able to link f1.o, f2.o, -o, myxz. So you see multiple definition of strong symbol x, which is not allowed by the linker. Let us see another example in which we have a strong and a weak symbol. Let me clear screen, move on to the other example. Here again we have two files. Let me see cat f1.c first. Sorry. Okay, over here we have two initialized global variables, x1 and x and y, x having the value of 1 and y having the value of 2, and both of these are strong symbols. Okay, fine. Let me view the code of f2.c as well. Over here I have a weak symbol, an uninitialized global variable x. Also note that it has a data type of float. Now we know that rule 2 of linker says in case of strong and multiple weak symbols, the linker choose the strong symbol. So while assigning 5.4 to the weak symbol x in this module f2.o, the linker will quietly choose the strong symbol x in f1.o. Let us compile and link this program. gcc -c asterisk.c. The object files have been created. Let me do gcc asterisk.o, and it is again a success. We have the executable with us, and you see the output. So instead of 1 over here, you get this value. Let me show you the code again. f1.c. So we have x is equal to 1, y is equal to 1. This function is called, which is there in f2.c, and then I'm printing this. So for the programmer of this file, who has coded this file, he will be expecting x is equal to 1 and y is equal to 2, while the output is a bit different. Let me do cat f2.c. Let's suppose that this file has been coded by someone else and he has used this symbol x again, and he has assigned this 5.4, and so you see this nasty bug. Well, dear students, this is a real nasty bug. It is just a two-module program, f1.o and f2.o, but in large systems with hundreds of modules, This kind of bug is extremely hard to fix. So what is the solution? The first thing you should try that you should not use the global variables. Always try to avoid the use of global variables. If you cannot do that, use static keywords with your global variables to make their scope local to that module. So if we have a static over here and a static over here, this bug wouldn't have been there. Another solution can be always initialize your global variables, thus making them a strong symbol. This way you will get an error while linking. If another strong symbol with the same name exists in some other module, which is written by maybe some other programmer. Okay, so far so good. Let me move back. Enough with the linker relocation and symbol resolution concept. Let us move ahead and try creating and using our own static libraries now. Well, this slide shows how the static version of the standard C library is created. What we do is we define all the functions in appropriate .c files. For example, a to I.c contains the code for ASCII to integer. Printf.c file contains the code for printing characters on the screen. Random.c again contains the code for random number generation. We compile these files to the appropriate .o files, and then we use the Unix tool AR, also called the librarian or archiver, to create our library with the name of libc.a, and this file contains all these .o files, and we call this the static version of the standard C library. And of course, every library has one or more associated header files which contains the function declaration. Let us move on to the terminal and see the main page of AR now, so that we can create our own static library. Man AR. Okay, so it is used to create, modify, and extract from archives. Please do read this man page and see the different options that we can use with the AR command. Let me quit and let me move 3 steps up and do this directory static lib. Let me do mkdir temp, and let me first extract all the .o files from the standard C library. And we know the standard C library is located in usr lib x86 64 Linux GNU libc.a. This AR utility is the archiver or librarian utility. -x option to AR tells to extract all the .o files from this library to the present working directory. Let me change my directory to temp, and then I should execute this command so that these should be there. Okay, now let me do ls. You can see these are the .o files. A lot of .o files which are there. Okay, let me see the count of these files. Clear screen, ls pipe wc. So there are 1576 relocatable object files in the standard C library. Let me do ls grep print f.o, and you can see we have this file printf.o. So -x option of AR can be used to extract the .o files from the library. You can use -t option as well, which just display them on std out. Okay, so enough. Let us now try creating our static library. To save time, I have written a program. The program consists of multiple .c files, my add.c, my div.c, my mul.c, and my sub.c, and a header file, my math.h. Let me view my math.h first. Well, you can see this header files contains function declaration for the 4 functions, which are passed 2 arguments, and they return the answer of those 2 arguments after adding them, subtracting them, multiplying them, or dividing them. Let me show you the code of my add.c. Very simple code. My sub.c, my mul.c, and my div.c. Okay, let me clear screen. The first step is to create the .o file. So let me do gcc-c static.c. So this will create 4 .o files. The next step is to archive all these .o files and create a library. AR is the command, hyphen RS is the option to create the library. R option will create the library, while S option will generate an index to the contents of this archive for speedy linking. Well, some people use ranlib tool for this task. Anyway, this is better. Hyphen RS, and then I need to give the name of the library, lib arifmath.a. Remember, gentlemen, you need to start the name of your library with this prefix, and you need to end it with .a extension. And this part is actually the name with which this will be linked by GCC. Anyway, so we want to add my add.o, my sub.o, my div.o, and my mul.o. These 4 .o files will be placed over here, and a library will be created. You can see that libarifmath.a has been created. Let me use ar-t and see the contents of this library. You can see these 4 files are there in it. Okay, now we have created the static library. Let us write a driver program and use this library now. Okay, so let's suppose that we have a prog1.c. Let me cat it. So this is again a very basic program. At the top you can see I have included mymath.h, and then over here I am using my add, my sub, my mul, and my div function, and I am displaying the results. Okay, let me do gcc-c prog1.c. Oops, I've got a fatal error, mymath.h not found. Well, dear students, by default, the GCC looks for the header files at the standard location, that is USR include. So one way is you should copy this mymath.h from this static library to that standard location. And the other option which you can use is you can mention to the GCC using the hyphen capital I option, and after capital I you need to give the path of the location where it should look for the header files, and that is one step up. That is, the header file is there in static lib. So let me press enter. This time it will not give any error, and you can see prog1.o has been created. Let me see the symbol table of prog1.o. You can see these all are undefined. These are not defined because the definition of these functions are there in lib arifmath.a, and the definition of printf is there in libc.a or libc.so, whatever. Okay, let me do gcc prog 1.0 and let me name it myxz. And you see, once I try to link it, it has not given me any error of printf, but it has given me error on these four symbols because uh, GCC implicitly link every program with the standard C library. You don't have to mention that. But for your own libraries, you need to explicitly mention the name of the library, and the option used is hyphen L, small l, and after that you need to give the linker name of the library, and that is Arif Math. Let me press enter now, and now it says it cannot find a Arif Math library. This is because GCC is searching for this library in the standard location, and that is usrlib. So one solution is you copy your library to the standard location, and the other is you tell the GCC using hyphen capital L option that please search for the library at this location. You can give the absolute path over here because it is there in this directory, so I have just said dot dot forward slash. Okay, you can see myxz has been created, dot forward slash myxz. Let me enter the first number 5, second number 3, and it has given you the result after adding, subtracting, multiplying and dividing these two numbers. Okay, dear students, let's change gear, move back. Okay, so this is the same thing which we have done. .o files, we have used the archiver to create the directory. We have written our driver program, and then we have linked this driver.o with the libarifmath.a and the libc.a, and finally the executable has been created. Okay, so this is AR tool. You can create, extract and display the library contents. The linker's algorithm for resolving external references. Let me read it out for you. It scans all the .o files and .a files in the command line order, and during the scan keep a list of the current unresolved references. As each new .o or .a file is encountered, it tries to resolve each unresolved reference in the list against the symbol defined in obj. If any entries in the unresolved list at the end of the scan, then error. So that means the command line order matters. Whenever you are doing linking, it matters that with which library you're linking first and with which library you're linking later. So it is always better to put the libraries at the end of the command line. Okay, so these are the limitations of static linking and the modern solution, that is the shared libraries. We have discussed these before. And let us move on to creating our own dynamic libraries, continuing with the same example. Well, dear students, a shared library is similar to static library because it is also a group of object files. However, a shared library is different from static library as the linker and loader both behave differently for a dynamic library. So in order, if you want to create a dynamic library or shared object, the step one is to create .o files using the -fpic option to GCC. Well, this -fpic option to GCC tells the compiler to generate position-independent code. And position-independent code is a code that can be loaded and executed at any address without being modified by the linker. And in step 2, you use -shared option with GCC and create the shared object file. Let us move on to the Linux terminal and do this. Let me do change to this. Let me do ls. So once again, we have the same example, same piece of code. I don't think that I need to show you. My math.h of course contains the declaration, and My add, my div, my mul, and my sub.c contains the definition of the functions. Let me create .o files with -f pick option this time. -c -f pick asterisk.c. So we have these .o files, but this time they are compiled with -f pick option. Now let us create the shared object file from these .o files. Gcc -shared static.o -o arifmath.so. Okay, so I have used -shared option with GCC to create the shared library, and I have said it that create a shared library and put all the .o files in the present working directory in it, and the name of the shared library is of course libarifmath.so. Remember, we need to put a lib in the beginning and .so at the end, and actually this is the name of the library that we will be used for linking. Let me press enter. Let me do ls. You see we have successfully created the dynamic library. Okay, so now let us see the disassembly of this shared object file to have fair understanding. Obj dump. Let me use obj dump -d -m arifmath.so, and let me do pipe this to the less program. Okay, so you can see the disassembly section of .init first. Let me search for my add. Okay, enough. You can see the assembly of my add, and you can see the assembly of my div and my mul and so on, my sub as well. Okay, fine. So we have successfully created a shared object file, and let us now write a driver program and use this. Cd to driver, clear screen. Okay, proc1.c. Once again, this is the same program, no change. The same program, same driver program which we have used for the static library as well. Let me do gcc -c proc1.c. Once again, the error of the header file is there, and I need to use the -I option, and I have to tell it that the header file is there in this directory. So I have gone one step up. Okay, so it has successfully created the .o file. Fine. Now I need to do gcc prog 1.o -o my exe, and naturally it will give me error, and now I need to tell it that you need to link it with the library whose name is arifmath, and again it will give us the error, and now I have to tell it please look for this library not in the standard path but at this location. Finally we have the executable. So the final executable has been created. If I do file my exe, you can see this file is a 64-bit file in ELF format which is dynamically linked. Let me also do ldd my exe. Well, ldd is a command that is used to list the dynamic dependencies of an executable file. You can see it depends on libarifmath.so, along with few other shared object files like Linux VDSO and libc.so and so on. Let me clear screen, and let's see the symbol table as well. nm my exe. You can see we have the my add, my div, my mul, my sub. These are still undefined. In case of static, if you see the symbol table of the executable, you will see a D over here. In case of dynamic, you see a U over here, because this is dynamically linked file, and the linking will be done at either load time or maybe at runtime. Let us see this now. Okay, so let me run this file ./myexe. So once I run this file, you get an error while loading libarifmath.so. It has not given me error of loading libc.so. It has given me error libarifmath.so. The reason is the loader is also searching for the libraries at standard location. So one solution is you either copy this library, that is libarifmath.so, from wherever location it is residing to the standard location, that is /usr/lib directory. And the other solution is you update the environment variable ld library path. Let me do that. Let me do export ld underscore library underscore path and put in this variable whatever is there in this library, in this variable before, and then let me put the absolute path this time of the location where this libarifmath.so is residing, and that is in home Arif SPVL system programming video lectures, and over there we have 03, and then we have dynamic lib. So this is a path. And now since this environment variable contains the path of this location, so now when I do execute my executable, the loader will search for libarifmath.so from this location, and so it will run successfully and will not give any error. Okay. Well, this slide shows a pictorial view of what we have done for the dynamic linking example. Fine. Okay, dear students, that is all for this session. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time, and until then, happy learning and Allah Hafiz.